Hey everybody, I'm re-recording a little bit of the yesterday's lecture because it came out really echoey, and I think I can do a little better with this external microphone. I also ordered a really good microphone on the internet, and it should arrive in a few days, so got that coming too. So I'm not redoing the entire lecture, just a little bit about, kind of in the middle of the lecture about HPLC and some of the radioactive analytical techniques. All right. So anyway, HPLC is one of the methods. Like kind of normal HPLC, we use UV vis detection, UV visible. So compounds absorb light in the UV visible spectrum, and we can detect them. Right. So this is I added the structure of Tylenol, which is also called paracetamol. And this just shows a kind of an example of an HPLC analysis of Tylenol and how it, in this case, comes at about 3.6 minutes. So it's passed through a little column that purifies and separates your compounds based on polarity. Very polar things are on the left, very nonpolar things are on the right, and Tylenol comes kind of in the middle of that. And this is a nice analytical technique based on UV visible detection. And this shows the UV vis spectrum, which it varies, right, based on wavelength. And there's a lambda max, which is kind of the maximum absorbance point, which is around 240, 250 or so. And for most organic molecules, we just set the absorbance frequency to be around 254 nanometers. I think that's the magic number, 254 nanometers. And anyway, yeah. So that's how the compound like Tylenol would be detected. This is what an HPLC looks like. It's a multi-component system where you have solvents up on the top, which are pumped through the machine. The typical solvents we use in our own HPLC when we do analysis is acetonitrile, right, CH3CN, which is one of the standard solvents. We also use water, so we use mixtures of water and acetonitrile. That's kind of pumped through the machine through a pump mechanism, and then there's an auto sampler. You can fill this up with samples and to do analysis. It's all robotics, so you can put like 1,000, not 1,000, but like maybe 100 samples, little tiny samples in here, and have this do an automated analysis of every one of them. And you define that all in the computer. You're like, all right, I have 20 or so samples, and these are the codes and the names of them and the vial locations, and then the auto sampler will actually find each sample and run it through the machine. And then there's a couple more steps, and there's a column. A column is the device that actually does the separation. I'm not going to get into all of that, but you've probably learned that somewhere. But yeah, the column is a small little linear device that your compound interacts with as it flows through the column, and then that's how the separation occurs, and how we get the polar compounds on the left and the nonpolar compounds on the right. You could probably, if you're interested in that, do a YouTube search for HPLC column theory maybe, and see more about it, or I could tell you more about that or give you references on that. And then from there, after it goes through the column, it goes into a detector, which is on the bottom. The detector is what actually detects the UV absorbance, and you select a wavelength. You're like, I want 254 nanometers, and then this is the full spectrum. But when we do the analysis, it's only based on a single wavelength, which is around 254 is the magic number that most people use. Even though this is not exactly a 254, it's a 243. I think in general 254 is a very common wavelength that works really well for people. Okay, What are the disadvantages? Well, I mean, this looks wonderful, but this is a pure compound, right? This is a single compound that we're just testing the machine with, and we see a nice peak. But when you have blood and urine or other biological fluids, those contain a lot of other things, and they all absorb at 254 also. So your HPLC turns out to be a mess. You have a whole bunch of peaks, 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 and then it's kind of hard to see what you want to see, which is maybe the drug, like you're trying to analyze, right? So there's a background issue with HPLC. So generally speaking, in a biological setting, we cannot detect low levels of substances this way. This is a wonderful technique, like when we're doing chemistry and or organic synthesis, where we're just trying to identify compounds and see if compounds are pure, etc. So in a chemistry setting, HPLC is amazing, but in a biological setting, we can't really detect low levels of substances this way. Another cool thing that we can do, I don't have a nice figure for this, but coupling an HPLC with a mass spectrometer, mass spec, which when you do that, HPLC plus mass spec, you get something called LCMS. And what that does is it's another piece of equipment that sits over here next to the HPLC, and that does mass spectrometry, which will tell you the molecular weight of the peaks that are being analyzed, and you can often sort of weed out your compound of interest or like a metabolite or something based on its molecular weight. So you can configure the mass spec and the software to show you just the molecular weights that you're interested in. So this kind of solves the problem of background. Not perfectly, but it's definitely one solution. And a lot of labs have mass specs and LCMSs, so it's a pretty easy solution to implement. Okay, so then the other idea is we can use a radioactively labeled molecule. And there's different isotopes of radioactive isotopes we can use. C14 is one of them. We'll talk a little bit more about C14 in this lecture, but it allows a much more sensitive detection using a scintillation counter. It's basically it detects the radioactive decaying particles, is what a scintillation counter is. If you saw that, I don't know if you saw that movie Chernobyl with the people walking around detecting radioactivity, those are all scintillation counters. But we can also do that as part of like an HPLC machine. So we could use a normal HPLC, but we can swap out the detector at the bottom for something like this, which is a Flowstar LB513 or LB500 radioactivity flow detector. So it's kind of like a little mini scintillation counter that analyzes the stream of liquids flowing through your HPLC, and then it would give you the same kind of chromatogram where you see your peak, and you can analyze stuff. This kind of solves the background problem also, because most of the molecules in your body are not radioactive, but your compound of interest, if it's labeled properly, would be radioactive. And then you basically solve the background problem that I was discussing. Hopefully that makes sense. But yeah, this is one of the tricks you can use. What are the disadvantages to this? Well, first of all, advantage, it's much more sensitive, maybe even like 10,000 times more sensitive. I mean, it's you don't even have to use a completely radioactive substance. It's not like 100% labeled or whatever. As long as you get some enrichment of the radioactive molecule, and you have 1% or 0.5% of your molecules are labeled, then you get this kind of enrichment, and it's just much more sensitive, right? Disadvantage, there are some toxicity hazards related to radioactive molecules, but at the same time, we expose ourselves to X-rays when we get X-rayed at the doctor's office. So there are risks to radioactive molecules and like beta particle decay and things, but we're also, there's acceptable levels of risk. So toxicity can be an issue, but often we can still use these kind of molecules in analysis. Sometimes it's synthetically challenging to make radioactively labeled molecules. Sometimes synthesis is, it can be difficult, it can be easy. Kind of depends on, the building blocks you're using to make your molecules, and if you can find a radioactively labeled version of those molecules. Sometimes that's challenging. Okay, so background on C14. First of all, it has a long half-life. So, and by half-life I mean the amount of time it takes for it to lose half of its radioactivity, or degrade half of the amount of C14. It's 5,730 years, 5,730 years. And so it decays kind of gradually. It's still useful to be analyzed, because when it decays and you're detecting beta particles, you can see them, pretty continuously. It's not like, it is a observable thing, and we can detect our compound using a scintillation counter, even in an HPLC environment. It's pretty amazing, even though it's decaying at the half-life of almost 6,000 years. It's a beta emitter, so it emits beta particles which can be sensitively detected. This kind of shows what's going on. So C14 degrades to 914. It's kind of weird. How's it gaining atomic mass? Well, it's, I believe that C14 has like 6 protons and 8 neutrons, and then the decay process is very complicated. So weird things are happening to the protons and neutrons, and for one, a neutron is getting converted to a proton, and that's how you go from C14 to N14. And also through this process, a beta particle is emitted, and that's what we actually detect. So and it's essentially an electron, and so we can detect these beta particles flowing out of our sample, and that's how we detect them, right? Okay, and what are other carbon isotopes? Of course, C12 is the normal dominant isotope of carbon. C13 is a non-radioactive carbon isotope, so it's got the normal number of protons, and it's got 1 extra neutron, but it's not radioactive. It doesn't decay or emit particles or beta particles. It's non-toxic. And so C13 is, you can detect C13 using mass spectrometry, and so that is kind of cool. So it has a sort of a special type of mass spectrometry that can detect C13, and since it's non-radioactive, people maybe like to use C13 as another option instead of C14. Drugs can be labeled with C14. Sometimes it's easy, sometimes it's maybe more challenging. If a molecule is produced as a natural product, naturally using enzymes, then you can kind of just use the building blocks, provide the building blocks that are enriched in your radioisotope. So this is an example of the biosynthesis of penicillin derivatives, and like this general penicillin scaffold. If we want to make it, we don't need to mix reagents as such and do a multi-step synthesis. All we have to do is throw in the 3 different building blocks, and the fungus will actually do the biosynthesis. And so all we do is we can obtain like radioactively labeled phenylacetic acid, radioactively labeled cysteine, and radioactively labeled valine, And these three building blocks, when you combine them and feed them into the fungus, will generate penicillin, and that's kind of cool. What else? And also, like, do you think that the fungus recognizes the differences between a non-radioactive substrate and a radioactive substrate? It doesn't care about the presence of extra neutrons, and so this does the work and prepares the molecule the same regardless. If it's a fully synthetic molecule, like a lot of the molecules we talked about in this course, we can use similar strategy but using radio-labeled building blocks. So we can carry out the full synthesis and then just use building blocks that have the radio label in them. This is an example of another antibiotic type derivative. This is Zyvox or linezolid, and just as an example, you can take these two molecules and they attach. The mechanism is a SN-AR reaction, nucleophilic aromatic substitution, or SNAR. The nitrogen attacks the carbon and the electrons flow over to the nitro, and then the nitro kicks them back and kicks off the leaving group, and that gives you the product. So we've talked about that, and it's also in the later part of your organic book. And then we reduce the nitro group to NH2 using H2 palladium. And then we attach this stuff. It's called benzyl chloroformate, which is actually a protecting group. This will protect the nitrogen. So, and this is actually radio labeled. The star is the radio label. And so the nitrogen would attack the carbon, and then electrons go up, down, kick off the chlorine, and then now the nitrogen has this protecting group on it. This benzyl carbamate. This is also called CBZ. We'll see CBZ later in the lecture. So when we hear about CBZ, this is what CBZ is. It's actually, the CBZ is everything to the right of the nitrogen. CBZ. Okay? And it can be taken off. You can remove a CBZ protecting group also with H2 palladium. So we used H2 palladium to reduce nitro, and also H2 palladium is what you would use to take off a CBZ group. Okay? So there's a couple steps we're omitting, but it essentially builds this little 5-member ring and an H2. The star stays along for the ride. That carbon remains radioactively labeled. And then amine, this primary amine would attack acetic anhydride, but this is acetic anhydride with radio labels on the two carbons. So remember that with acetic anhydride, it's like we could attack the right side carbonyl and then kick off the left side thing as a leaving group. So, right, nitrogen attacks, electrons go up, electrons go down, kick off the oxygen, and then that goes away as a leaving group. So your leaving group is actually radioactive here. It's disposed of properly. But then we have our product, linezolid, and we have two radio labels, and those allow us to sensitively detect this molecule, not only this molecule, but also its metabolites. So if this gets metabolized, maybe at a high oxygen, or if this gets cleaved off during metabolism, we can track each of those molecules because they're all radioactive, which is cool. So anyway, that's an example of either the biosynthesis or the kind of multi-step normal synthesis of a synthetic molecule with the incorporation of radioactive building blocks. And you can purchase a lot of radioactively labeled building blocks. Sometimes they are produced in a synchrotron or some kind of radiochemistry facility. So there's specialized facilities that generate molecules like this. And they have to use some pretty crazy magic to install the carbon radioactively labeled. But that's a whole area of science. You could totally be a career, you you could develop a career as a radiochemist. And there's even PhD programs in radiochemistry. It's a pretty cool area to get into. Not a ton of people are in it, so it's pretty easy to get a long-term job or career as a radiochemist. We'll talk a little later in the lecture about some really cool work in the Department of Radiology at UCSF that uses kind of radio labeled molecules to do PET imaging, positron emission tomography. And they are doing organic chemistry in the Department of Radiology to do imaging of like cancer and diseases and stuff with radioactively labeled compounds. Okay, so that's later in the lecture, near the end, I guess. Okay, and then one use of C14 is urea C14. Urea C14. And this is used to detect H. pylori, which is a bacterial infection in the stomach. And you'd be administered urea C14, which is urea, which is NH2, C double bond O, NH2, with the carbon radioactively labeled. And then there's a trick to basically analyze that through exhaled CO2. This is what it looks like. So here's the C14 urea. So there's urea with the C14 label. You eat it or consume it, and it enters your stomach. And the trick here is that H. pylori has enzymes in it, in the bacteria, called ureases. What does that do? Well, that hydrolyzes urea, and it creates ammonium, the nitrogens, and it makes basically C14 labeled bicarbonate. And that's what this is. This gets kind of metabolized and pushed through your system and into your lungs, and then you breathe it out as C14 labeled carbon dioxide, CO2. And then you blow out into a balloon, and there's a couple steps of processing into a scintillation counter, and that detects if you have C14 CO2 in your breath, which would be an indication that you have this stomach infection. So it's a kind of pretty cool trick to figure out if you have infection. And more recently, people have kind of replaced C14 urea with something called urea C13 or C13 urea. And it's the same thing, but uses C13, which is non-radioactive. And you would detect the presence of CO2 labeled with C13. And we don't use a scintillation counter because there's no radioactivity. We'll use mass spectrometry. Okay, I think that's where I'm going to stop. I think the majority of the echoing that I had earlier was stopping right about now. Pretty sure that's the case.